In this video, I want to discuss what is meant by a divergent transition in Hamiltonian Monte Carlo, and secondly, what can we do about these sorts of iterations. So firstly, we're going to start off by discussing what do I actually mean by divergent transitions. I'm then going to discuss the potential causes of such transitions in Hamiltonian Monte Carlo. I'm going to discuss why this is in fact a problem, and lastly we're going to talk about how we can actually remedy this problem in practice. So remember, in Hamiltonian Monte Carlo, essentially what we have is we imagine we have a position of our particle at a given point in time, which is just given by theta, our parameter vector which we want to sample from. And we also have a potential energy function, which is defined for every value of theta. So an example potential energy landscape might look something like this mauve line, which I'm drawing here. And in Hamiltonian Monte Carlo, what we do is we imagine that we've got some sort of fictitious particle, or I call it a sledge in the book, which slides over this frictionless landscape. And the idea is that if we give this particle here a little push, then it will eventually reach the bottom of this potential energy landscape, and it will have a large amount of momentum at that given point in time. And then the particle will ascend this landscape. So it might get somewhere like this, and indeed in this case, because it's a frictionless landscape, it would indeed go over this trough or over this peak here that I've indicated. And the idea with Hamiltonian Monte Carlo is that the energy of our particle is partitioned into two different sources. So I'm going to call H here the energy, which I've previously written as E, but H is more common when we're discussing Hamiltonian dynamics, and it's just equal to the potential energy of the particle, which is a function of the particle's position, theta, plus the kinetic energy of the particle, which is a function of its momentum, m. And the idea with Hamiltonian dynamics is that the total energy is conserved, so that when the particle loses an amount of potential energy, this is converted into the same amount of kinetic energy, and vice versa. And we know that there are equations which, if we could solve them, would allow us to solve for the exact motion of the particle over time. So those are given by d theta I over dt, in other words, the rate of change of the position of the particle in the ith dimension is equal to the partial derivative of the Hamiltonian with respect to the momentum in that particular dimension. So I here is referring to the given dimension, so that's, for example, 1, 2, all the way up to the dth dimension if I'm talking about a d-dimensional parameter space. So that's the first equation of Hamiltonian dynamics. The second equation is an equation for the rate of change of the momentum in the ith direction, and that's equal to minus the derivative of the Hamiltonian with respect to the position of the particle in that dimension. And the idea here is that if we were to solve simultaneously these two equations, and if we could do so exactly, then we would simulate exactly the path of our particle on this potential landscape that I've indicated here above. The problem, however, is that we cannot solve these two equations exactly for most interesting problems. So what do? We end up discretizing them, and we use numerical integrators to solve these two equations. And the idea is that in order to ensure that we actually get a reasonable conservation of energy, we should use a class of numerical integration technique which is known as symplectic, of which the most common algorithm that is used, and indeed the one that's used in STAN, is the leapfrog algorithm. And so the idea is that rather than solving for the path of the particle exactly, which would give us a sort of smooth line between the positions of the particle, instead what we do is we discretize the particle's path into small discrete steps, and we essentially solve Hamiltonian dynamics for each of these discrete steps. And hopefully, if we choose our step length to be sufficiently small, then we get a pretty good approximation to the true path. In Hamiltonian Monte Carlo, whether we actually accept a given proposed value of theta, and indeed the momentum as well, is governed by a ratio r, which is equal to the minimum of, firstly we have the exponent of minus h primed minus h, where h primed is the Hamiltonian after we've followed the particle for a given period of time, and h is the Hamiltonian, in other words the energy before we started following our particle after we gave it a shove. So it's given by the minimum of this exponent term here, or 1. So this is the probability that we actually accept a given proposal. And one thing to notice here is that if we actually solved for the motion of the particle exactly, then in that case the energy is conserved, and so we have that h primed equals h. In other words, this whole exponent term here becomes the exponent of 0, in other words it becomes 1, and in that circumstance we always accept a given proposal. However, in practice, because we discretize the motion of the particle, we only approximate the path of the particle, and that leads to hopefully quite small variations in the Hamiltonian, but nonetheless those small variations in the Hamiltonian can mean that actually we reject a given proposal. The good thing about Hamiltonian Monte Carlo is that we can actually determine whether or not our approximation to the true path of the particle is reasonable by just examining the Hamiltonian before and after we follow the motion of the particle over time. If our discretization length is relatively small, then what we hope is that our deviations away from the true path tend also to be relatively small. So that's what I'm just sort of indicating here on the left. In this case, we don't quite obtain the true motion of the particle, but in each case we tend to be sort of correcting for the mistake that we made on the previous step. So we tend not to get too far away from the true path. So in this limit we see that the Hamiltonian at the end of the path, so that's at this point here, should hopefully be relatively similar to that at the beginning of the path. So they're not too different in value. In other words, the energy is nearly conserved. If we choose a larger step length, so that's what I'm indicating here in this second panel, then we see that the path of the particle is a less good approximation to the true path. But nonetheless, we still seem to be doing a pretty good job at approximating the path of the particle, and then hopefully, again in this case, we should see that the Hamiltonian at the end of the path is pretty similar to the value of the Hamiltonian at the beginning. So it looks like we're getting a pretty good approximation to what the path of the particle would actually go like. However, if we choose a step length which is too large relative to the curvature of the true path, then what we can actually find is that the approximate path that we estimate is not a good approximation to the true path. In fact, we could even say that the true path and the approximate path have diverged from one another. They are divergent. And in this case, what we would see is that the Hamiltonian at the end of the path is not similar to the Hamiltonian at the beginning of the path. And this is really important because in the case of these sorts of divergent transitions, we are not actually doing what we want to do, which is to use the posterior distribution to dictate where our particle should move to. So actually we want these types of transitions to be highlighted to us. And that's simple enough for us to do because all we do is we compare the Hamiltonian at the end with the Hamiltonian at the beginning, and if they're very different from one another, then we call that a divergent transition. And indeed that's exactly what Stan does. So what's the cause of divergent transitions? Well, the idea is that if we have a posterior curvature which is particularly strong at a given point in parameter space, so imagine that we have a posterior which looks something like this, which I'm drawing now, then it actually becomes very difficult for a discretization routine with a given step length to approximate this path in a particularly good way. So what we may find here is that we do pretty well in terms of following the path of the particle when it's over in this region here, but perhaps when we get to this area of very high curvature, then we might actually end up following the particle's path, or approximating its path rather, and we can see here that we've kind of moved away from the underlying potential energy landscape. And we can see that this region of sharp curvature has actually caused us to fail here. So, in summary, the cause of divergent transitions is a sharp curvature at a given point in parameter space. And in particular, it's a sharp curvature relative to the step length. Because if we were to use a much smaller step length here, then perhaps we would actually do a much better job of approximating the true path of the particle. But because we used a larger step length, we stepped too far, and in fact we overstepped here, which led us to this region of our path of our particle, which actually is quite a long way away from the true path. The reason that we might have a step length which is too long for a given point in parameter space is that most of these algorithms, and Stan is no different, hope to achieve a global step size which is optimal. And in hoping to achieve a global optimal step size, that doesn't mean that we will obtain local optimality. And indeed, at given points in parameter space, the step size may be too short, or indeed it may be too long. If it's too long, then that can lead us to diverge away from the true path of the particle. If it's too short, then that just means that we're being inefficient with our computation. So a question you might have is, well, why do I care? What's the problem with these divergent transitions? Well, it's a problem because essentially that means that in these regions of high curvature, we are getting divergent iterations, and essentially in Stan that means that we get a bias away from these regions of high curvature. And anytime we have this kind of bias, we should be a bit concerned, because not only are our posteriors not necessarily of the correct sort of shape, but also the summaries of those posteriors may be quite misleading. So now if we talk about the remedy to divergent transitions, then an obvious one is to just use smaller step sizes or step lengths. And indeed in Stan you can manually specify a step length, and that's certainly something to try if you have sort of minor issues with divergent transitions. A more thorough way to deal with divergent transitions is to respecify the model. And in particular what we're doing is we're respecifying the model to avoid these regions of high curvature. And that really comes back to something which Gelman calls his folk theorem, which is that essentially any problems that we have with sampling from a given statistical model often reflect problems with the underlying model itself, not with the sampling algorithm. And with divergent transitions, that's particularly true. These tend to occur in hierarchical models and in models where we're lacking identification. I finally want to illustrate an example of a model which exhibits divergent transitions. And the example model that I'm using is kind of deliberately pathological. So what we're going to imagine here is that we have some data xi, which is being normally distributed about some mean which is given by the product of two things. One of them is a parameter n, which here refers to a kind of population size, and rho, which occurs to the rate of occurrence of particular events that we're interested in. And we're imagining that this normal distribution has got some standard deviation sigma. And I don't want to discuss now the particular priors that I'm using in this model, because you'll see that in a second. But what I want to comment on is why this model is pathological. Well, the idea here is that a given mean of our normal distribution can be obtained in two ways, because of the fact that our mean n times rho being equal to a constant which I'm going to call c here can be obtained by a infinitum of different values of n and rho. Indeed, anywhere along the curve which is given by c over rho, or n is equal to c over rho, do we obtain the same mean. Why is that problematic? Well, the idea here is that what we could do is we could draw a graph of rho against n, and we could draw this curve here, which would be a downward sloping line, which is given by this sort of mauve line which I've drawn here. So for clarity, this is given by the line n equals c over rho. So why does this sort of model exhibit divergent transitions? Well, the problem is that in the tails of this kind of distribution here, which are kind of going to be, or whatever the posterior distribution is, it's going to be kind of concentrated along a kind of shape which looks something like this downward sloping line here. In the tails of this distribution, it makes sense to move quite long step lengths, at least in terms of, in this case, n, and in the other case, the other tail, in terms of rho. So we quite like to use long step lengths here in n and rho respectively, and small step lengths in the other ones. But however, when we're in the middle here, small changes to either n or rho can result in different means. And so we want small step sizes here, because our mean is essentially more sensitive to changes in n and rho. And so we see that what we'd like to do is we'd like to essentially use, for at least one of the parameters, big step lengths in the tails, and we want to use small step length in the middle. And that's problematic because of the fact that essentially by choosing a single global optimal step length, that means that in the area where small changes in n and rho have big effects on the mean, we may be stepping to large distances relative to the curvature of the posterior. And so we get divergent transitions in the kind of neck region of our kind of posterior distribution here. A way to remedy this problem would be to use more stringent priors on either n or rho, because then what we end up doing is we end up localizing ourselves to one area of this kind of downward sloping posterior space. So now I want to illustrate using RStan how such a model will exhibit divergent transitions. So we're supplying some data, we've got our three parameters here, n, rho and sigma, and below we've got our model which I've written in vectorized form, or the likelihood in vectorized form, just as this, and we have got some fairly wide priors on each of our parameters. So now, after having compiled that model, I can sample from it using Stan, and hopefully what we should see here, if we look in the list of warning messages, is that we get some warning about divergent transitions after warm-up. And Stan actually suggests what we might do in this circumstance. What it suggests we do is we increase our adapt delta above 0.8. What does that actually mean? Well, essentially it means that we're going to try and target a global step size which results in a percentage of accepted proposals which is greater than 0.8. And so the way in which we do that in RStan is we specify an argument control which is equal to a list, and I'm going to include here adapt delta, and I'm going to say adapt delta is equal to 0.95, because essentially by targeting a higher acceptance rate, that should lead us to have a smaller step size. You can also specify manually a smaller step size here, as I indicated before, but often I found with this sort of minor divergent transition problems, perhaps adapt delta being equal to 0.95 is sufficient. So if we rerun this model, hopefully what we should see after this model has run is that we get fewer divergent transitions. In fact, we've got 0 divergent transitions now. So it looks like just increasing adapt delta to 0.95 has done the job here. Another way to avoid this issue here might be to use slightly more stringent priors here. So potentially we might have more knowledge about n, and we might imagine that n is slightly more confined in parameter space. And similarly for rho we're using very, very wide priors here. So we might say that rho is somewhere like that, so it's got a width of 5 rather than of 20. I won't rerun this model now, but if you want to try this for yourself, hopefully you should see after we change these priors that we no longer see this issue of divergent iterations. Whilst I've illustrated here that changing the tuning of our sampling algorithm can indeed allow us to avoid these divergent transitions in this simple case, in more complicated cases, typically hierarchical models, such a tuning change doesn't actually result in us avoiding the issue of divergent transitions. In those circumstances, we'd generally be better to reparameterize the model. And exactly how we do that depends on the particular circumstance. So in summary, we've found that divergent transitions arise when we use a step size for our Hamiltonian Monte Carlo discretization that is too large relative to the posterior curvature at a given point in parameter space. Divergent transitions are a problem because of the fact that essentially that means that we get a bias away from certain areas of parameter space. The remedy for these types of problem is either to specify a smaller step size, which we can do quite easily in Stan, or a more general and more thorough way to reduce this issue of divergent transitions is to reparameterize a model.